It's you do not need any cancellation. It's visible from the start. Should I explain that? Or?
Oh yeah, we had 10 more minutes, so it should be.
Yeah, no, it's just not to interrupt. You might be later, but you see that if you look at spinor indices of muon, and when you're constructing this loops or effective operator, you can see that these indices are between right and left are convoluted. So it's only spin zero there, and it could not be a dipole moment, magnetic moment at all, because it is, you see, it's convoluted indices. So it means that your integration by parts is already done, and it is zero.
So we still have the following operator. Let's see. Is this visible, or should I turn on the? I agree. Are you talking about the absence of integers?
Yeah, no. But look, you can write effective operator. This, for example, right away, and the effective operator would be containing Higgs field 3 times. When you integrate,
this one.
Right, but F mu should be convoluted with spinor indices, right?
We have another operator here. So this also contributes to G minus 2.
Which one?
This upper one, the one without the Pauli matrices.
No, but this you can rewrite the same way. Yeah, it is kinematical. I disagree. There is only one operator because they are dependent. So in this way, it's not independent operator. And when you're constructing, your loop or whatever, let's say that you're integrating over heavy quarks, okay? So what you will get? You will get a Higgs field 3 times, right? But spinor indices of right and left would be convoluted.
I agree. So that's why we have this diagram.
Right. But then it doesn't contribute to the magnetic moment.
No. This does contribute to magnetic moment.
No. It is. Look, if you have psi alpha, in this sense, how to say, you have a convolution the same as a mass term. It is scalar.
I agree. I completely agree. But my claim is that this operator contributes to G minus 2.
I do not see it clearly. Okay, because if you have a convolution of mu bar mu, it is a mass term, right?
Yeah. But do you agree that the first operator could be generated?
Can you read what is it? Okay, just a moment.
So here, spinor is contracted trivially.
Okay.
Yeah.
No. But look, this one it is a charge, right? So of course gamma mu contains there is a term which gamma mu, which is normal electric charge of muon, right? So this normal magnetic moment, it's not G minus 2.
No. This contributes G minus 2.
No, but you can rewrite this as gamma mu term and F mu term.
After you remove that, then using equation then you obtain this.
Yeah, but if you take my impression is that if you I do not see how you will get D if you integrate heavy quarks out. What you will get? What operator?
This operator.
How you will get how you will get derivative this covariant derivative?
It's just the derivatives, it's just momentum dependence.
No. But if I'm integrating heavy quarks, the main term would be the one where there is no derivative, because you're just substituting heavy quark. I mean, relating 1 over mass, right? You expanding it in mass. And if you do this expansion, then you will get, I mean, in the simple form, you will get Higgs field cube and convolution, and the part which is kind of left bar multiplied by right bar mu, okay, which is like a mass term. And this term, certainly you would agree that it's not the one which contributes to, it's before taking photon, before photon. Okay, so and then you, whatever you do with the loop, it doesn't help you.
But no. As if you have a diagram, so then if you expand with respect to the momentum of the...
No. Okay, first of all, consider three diagrams, three level diagram. And integrate out heavy quark. Okay, then what is the leading term? The leading term, 1 over mass of heavy quark, right? Multiplied by something. And you can integrate both your L quarks and S quark, integrate both. So you will get 1 over ms and 1 over ml, and then something there. And it's what I am describing. It is this some, and it is 3 level. It's not a loop.
Yeah. At 3 level, yeah. There's
okay,
no
and at this 3 level, you have only spin 0. You do not. Spin 0 between this muonic, wave function. So then whatever you do with the loop would not help you to get magnetic moment.
So no. So then you must look at the next operator. If that
but next it would be a higher dimension. I am talking about the first.
If you use higher dimension operator, then we should take care of that.
Okay, but
quadratic divergence.
Okay, but this one loop vanishing is related to what I am trying to say. Because in this way you can consider not loop but this integration of heavy quark, and then of course once you get this spin 0, then loop would not help you. When we go further, when you expand further and consider derivatives, then it could be what you showed in higher orders. I'm not arguing about this.
Even if you use a higher dimension, higher derivative operator, so now you have to deal with the quadratic divergence if you want to use the low energy effective field theory. So you can simply look at the leading lower dimension operator to argue that vanishes should vanish.
Yeah. So because you were discussing that it's surprising kind of no symmetry relation, I'm trying to say that it's not surprising. Okay, it's not about your higher dimensions. It's about. Okay, I'm sorry that I started to do that.
Yeah, but maybe that Keisuke start to share the slide because the seminar.
Okay, I'm sorry.
Yeah, and then you should ask during the talk. You can feel free to ask during the talk. I think Keisuke can share that. And you can share the screen. Go ahead.
Okay. Yes. Okay. Can I share the screen or? See.
Not yet.
Okay. Cancel.
I think you haven't shared the screen yet.
If I share the screen, what you are not sharing will disappear. Is that okay?
Maybe, let's see.
Okay. Okay, can I share my screen?
Yes, no.
Mm-hmm. Can I start?
By the way, I'll introduce you. By the way, are you leaving at some time? Like because you say you have some duty.
Yeah, I have to pick up my kids before 6 p.m. Yeah, that's why I ask you to start a bit earlier.
Okay. Yeah, so maybe we can briefly start. Welcome everyone. Welcome to our quantum matter in math and physics seminar series. Today we are very honored to have a topics on again a muon -2 and this theoretical topics that Keisuke Harigaya will be presented. Keisuke was a colleague at IS a few years back, but currently he was moved to CERN, and he will speak about naturalness and the muon -2 work done with NEMA. Before I begin, I especially encourage the audience, and presumably there will be more guests joining later. Please feel free to interrupt and ask questions, and also welcome. Okay, Yokoso, please take over.
Hello, I'm Keisuke Harigaya. So thank you for the invitation to this seminar series. So today I'd like to talk about some naturalness and muon G-2, so anomalous magnetic moment, based on the paper with Nima Al-Ghani-Ahmed. Okay, so here's a very brief summary of my presentation. So one, the observed muon anomalous magnetic moment, which is called G-2, which I will introduce, deviates from the standard model prediction. So two, so we analyze a simple natural theory that can explain the deviation. But three, so, however, the naively leading correction to the G-2, the anomalous magnetic moment vanishes, so violating the naturalness expectations. Then finally, I will explain some phenomenological implication of this vanishing G-2 as a leading order. So here is the outline of my presentation. So first, I will introduce what the G-2 anomalous magnetic moment is. So, and then explain the setup of our model. So then I will show the computation of the correction to the G-2 in that setup, and show that the correction is unnaturally smaller than the naive expectation. Then finally, I will explain the phenomenological implications. So, okay, let's start from the G-2. So G-2, so the generically the charged particle or the particle that has spin can interact with the magnetic field of the form spin times the magnetic field. So its coefficient is often parameterized as G. So using the Dirac equation, so in another word, at the 3 level for the charged particle, we can show that this factor G equal 2. However, after including quantum correction, such as a QED or electroweak quantum correction, this G deviates from 2. So we call this G-2 or anomalous magnetic moment. So we also use the notation G-2 divided by 2, which is denoted as A mu. So this G-2 anomalous magnetic moment is sensitive to the quantum correction. So its precise measurement can test the standard model or possibly reveals a new physics if that exists at a low enough energy scale. And of course, people have computed this precisely, and people have measured this precisely. So first, as was explained by seminar in this seminar series about 2 weeks ago, so there seems to be some tension between the standard model predictions and the measured value of the anomalous magnetic moment, which is formally about 4 sigma. It just means that this is 4 times larger than the error bar. So this may be due to some deficit in the standard model computation or possibly some experiment. But today let's pass to the possibility that this deviation is actually explained by some new physics beyond the standard model. So that's what we are going to do today. So first, let's do some analysis based on the effective operator. So the effective new physics at low energy, namely the energy scale at which deviation is measured, may be expressed by effective higher dimension operators. At the dimension 6 level, we have the following 2 leading operators. So here, can you see the cursor? I guess so. So here, E is a right-handed muon. Sigma is just Pauli matrices. And L is a left-handed muon that couples to the weak gauge boson in the standard model. So here, H is a Higgs. So we need this Higgs because right-handed muon is singlet of SU2, but left-handed is a doublet of SU2. So to compensate that, we need the Higgs. And of course, to have a G minus, we need a photon. This is one operator. So another possibility is the one with the Pauli matrix, but just derivative, covariant derivative on the fermions. So these 2 are the leading operators. So we have another dimension 6 operator shown at the bottom of the slide, but their effect are always suppressed by the small muon mass in comparison with the new physics scale. So these are typically negligible. So we will focus on these 2 operators shown at the top of the slides.
Why you're, I'm sorry to interrupt, but D square act on what?
Sorry.
D square.
D square.
Yes.
So could you say?
X on what? D square. X on lepton. X.
Yeah, if you act by D square on L, then it's equation of motion, right?
So it is D slash square. Yes, it trivially vanishes via equation of motion.
D slash square. Okay,
D is not does not have a gamma matrix. It's really derivative.
So what?
So here D is not D slash, but really D.
Okay, but D square acting on what? On L or on H?
So it can act on both.
Okay.
Here, there's several possibility about that.
Okay. If in low energy physics, acting on H is not a subject.
True. Yeah, you can just ignore Higgs. Yeah.
When D square act on L, you can use equation of motion to express this as a first operator. So there is no 2 operators at low energy.
So still, so that we have. Yeah.
In normal D square, without slash, it is still, you can rewrite it as D slash square minus nu, whatever. And then you will see that it is the same operator as the first one, and H should be substituted by mass of particle. H, it is mass of muon.
After using equation of motion, yeah, I think I agree with
okay,
you.
So then statements about 2 operators is not relevant for low energy physics.
But still, this square after using equation of motion contains the first operator, so it still affect the G minus 2.
But it is the same operator because equation of motion is supposed to be fulfilled.
Using equation of motion, yeah.
All right, but yeah,
at the amplitude level, yeah, they are different.
Okay. So in this way, I would say that if I have to count operators, then I would say that it is dimension 5, not dimension 6.
Let's see.
Because H is just a number. So
I agree. But here I use this electric
of course you can say that it is 6 because it's multiplied by mass. But
I mean, typically I will consider the theory where new Higgs scale is above the electric scale. So this electric symmetric notation would be convenient. Yeah.
No, but still in the experimental way, you are substituting H by.
I agree. Yeah. I totally agree with you. Okay, let's proceed. Yeah.
Okay.
I agree that below the electric scale, we can just put Higgs at the wave, and we can just use dimension 5 operator. Yeah, I agree. Yeah. But later I will use the dimension analysis to put the new Higgs scale in the downstairs. So for that purpose, it is better to keep Higgs, as you know. Yeah. Okay. Thank you. Yeah.
Okay. Can I ask a question also? So what you said sigma is Pauli matrix, but you want like 4 by 4? It looks like this first operator is spinful, no?
So here, so I use a two component notation. So sigma is actually 2 by 2 matrix. So does that answer your question, or did I miss?
No, I don't understand what these indices are. Then, no, I don't understand how you get a singlet here, space-time singlet.
So we have mu nu. So this has two vector index. This is the just multiplication of the two Pauli matrix, and we have F here. So that's how we obtain Lorentz scalar.
Maybe the sigma mu is the I forgot actually.
Doesn't mu and nu range over 4 indices? I don't understand.
0, 1, 2, 3. Yeah. Actually, so here the Pauli matrix plus the sigma 0, the unit matrix. Yeah, which was formed to which I used to form Lorentz invariant quantity.
Can you remind us just your notation of sigma mu nu written in terms of the sigma mu, which mu is 0, 1, 2, 3?
So sigma 0 equals just unit matrix. Sigma 1, 2, 3 are proportional to sigma 1, 2, 3, the usual Pauli matrix.
That's no problem. But my question was, sigma, how do you write sigma up mu nu in terms of sigma mu? Maybe
so it's just sigma bar mu. It's sigma bar mu, sigma mu minus sigma mu, sigma bar mu, and sigma bar is defined so that the sigma 0 is
yes, no problem. Okay.
But I don't understand. Like you shouldn't be. There isn't a space-time two form that you can use here. This doesn't look Lorentz invariant to me.
No, but look, the simple way to represent what Keisuke is saying, use these spinor indices. Then you have EC alpha, L beta, spinor indices which 1, 2, okay, and F alpha beta. Where alpha beta it is this supersymmetric form of this F mu. Instead of F mu, the index is 0 to 3. You can use.
Oh, I see what you're saying. Okay.
You prefer spinor notation. Okay.
And it is very simple form, because you can immediately see that you have symmetric F alpha beta multiplied by this EC alpha L beta.
I agree. You can make it from the spinners. Okay.
Yeah.
But it is the same as as was said. It's just different notation.
Yeah. Thank you. Yeah. So let's see. Where are we now? Okay. So let me proceed. How can I proceed? So then when we try to explain a deviation of G-2 from new physics, what we do is construct a theory such that a quantum correction to the new particles or new interaction generate this as a quantum correction that can be expressed by this diagram. So left-hand particle muon, right-hand muon, photon, and Higgs. So anything could be inside this blob. It could be scalars, or it could be fermions, or it could be vectors. So the computation model is of course model dependent, but we can extract the naive expectation for the mass scale of the new Higgs in the following way. So from this diagram, let's just remove photon. So then this is nothing but the quantum correction to the Yukawa coupling between Higgs and muons. So that gives quantum correction to the muon mass. So this is dimension 4, correction to dimension 4 operators. So now putting back the photons, a photon, we obtain the dimension 6 operator. So then from the dimensional analysis, so we can just put the new Higgs mass scale in the downstairs and compensate it by the muon mass to obtain a naive expression, the naive relation between the correction to anomalous magnetic moment and the correction to the muon mass. So if let's require that this is as large as the observed deviation, 10 to minus 9. So if this the correction to the muon mass is one loop suppressed in comparison with the muon mass, which is the case when this correction itself is that proportional to the muon-Yukawa coupling. So then to explain deviation, we need a new Higgs mass scale around 100 GeV. But on the other hand, if the quantum the correction to the muon mass is as large as the observed muon mass itself, so this new Higgs mass scale could be as large as 1 to few dB scale. So from this, you can see that we will expect a new Higgs scale around the electric scale to the 10 times the electric scale.
You're saying those two corrections have to be of the same. You're saying those two corrections have to be of the same order, like the prefactors.
I mean this naive relation up to prefactor, yeah.
But look, it is just dimensional analysis because look, what scale you have? You have m mu and this new mass, large, big, capital M, right? The statement is that the answer is proportional to square of the ratio. Okay, and the proportionality to m mu square is follows from chirality, right? Essentially, so in this sense, then it's just about numerical coefficient, but the appearance of there is no any other low energy scale besides m mu if we are talking about this.
Okay, thank you.
What's this numerical factor? Could be 6 or 1/6. So yeah, this is no more than naive expectation, but we should actually compute diagram. Yeah. Okay. So then, based on this approximately of the electric scale and a new physics to explain the G-2 deviation of G-2, the people has considered the following what we could call canonical idea. So this new physics scale around the electric scale, a bit above the electric scale, explain both the origin of the electric symmetry breaking by the Stallman Higgs and the deviation of the G-2. So one famous example is supersymmetry, where the mass of the Higgs is basically given by the masses of superparticles. So in other words, SUSY breaking induce electric symmetry breaking. And the masses of the superpartners of lepton, Higgs, and electric edge boson give a quantum correction to the muon magnetic moment, as first considered by these authors. So this was the canonical idea, which dominated field maybe last 20 years or so. So that is this end of the overview of the G-2 and past works. So let me move on to what we want to do, the setup. So the canonical idea was, as I explained, connecting this muon G-2 with the electroweak symmetry breaking. But today, we'd like to consider the different possibility where we have so-called little hierarchy between the electric scale and the new physics. Yeah, so explaining the electric symmetry scale by new physics is a great idea, but unfortunately, so far no new physics that could explain the electric scale, the magnitude of electric scale have not yet been found at colliders so far. So based on the situation, we should seriously consider possibility that the cutoff scale of the standard model, which we can call lambda, is higher than the TV scale. It could be much higher, but it could be just a bit higher than a TV scales. So we often consider this situation the little hierarchy between the electric scale and the new physics scales. So one example, known example is so-called mini split supersymmetry, where the cutoff scale, the masses of superpartners are around 100 to 1,000 dB. So in this scenario, the electric scale is highly fine-tuned, but still it has some good motivation, like having dark matter candidates or successful gauge coupling unification via the quantum correction from superpartners. So
can I ask another naive question? So what would amount to an explanation of the scale? It would be to find some particles of mass around that scale.
Let's see. So could you repeat
what amounts? What does it mean to explain the scale?
Explain a scale. It's like obtaining that scale from other dynamics, like obtaining the Romeson mass or pion mass from the some QCD scale.
I see. So you will always shunt it to some other scale that you already have.
Yeah.
Okay.
So the idea is that want to have that scale naturally. So for example, we usually do not complain that the QCD scale is much smaller than the Planck scale. That's just given by the so-called dimensional transmutation. So when we say we obtain some scale from some dynamics, that's a basic idea. We want to explain the electric symmetry from some other dynamics, so that we can easily explain why the electric scale is smaller than, for example, gravitational energy scale.
I see. Thank you.
Thank you. Yeah. So let's see. So then, if this is a little hierarchy the case, if the scale, a cutoff scale, is behind the Higgs much larger than the electric scale, so how should we explain G-2? So we would explain. We would expect that new scalars would also have a mass scale as large as a cutoff scale. So they are too heavy to contribute to the muon G-2. And we could also consider vector, but to have vector, so since we haven't found them, we must give a mass to them. So we need some Higgs that give mass to vectors. So because that extra Higgs would be also heavy, we expect new vectors, if it exists, will also be heavy. So it is unlikely that new scalars and vector will explain this deviation of G-2. So we will consider the possibility that new fermions explain the deviation of the G-2. This is because the masses of new fermions are protected by the chiral symmetry. So their mass do not have to be as large as the cutoff scale of the theory. So we restrict the possibility to the case where this blob includes only new fermions and standard model particles. And such a possibility has been already considered in the literature. So for example, people consider the standard model plus SU2 left doublet Dirac fermion plus gauge singlet Dirac fermions. And these authors consider this possibility. And the generic interaction between those new particles and the standard model particles are, in addition to the gauge interaction, these four Yukawa interaction. So here, this arrow show the arrows show the flow of the chirality.
But Higgs is the same Higgs, standard model Higgs, or it's a new Higgs?
These are all standard model Higgs. We never introduce new scalar because we haven't observed new particles, new dynamics. Yeah. So let's only use Higgs. Yeah. So then with this interaction, and we can actually write down some Feynman diagram that seems to generate the muon G-2 or dimension 6 operators. So if we compute this, we will obtain the non-zero G-2. But let's compute that, but we will find a little bit of surprise. Okay, let's compute the muon G-2 in this setup. So it turns out that no dimension 6 G-mass operators are generated at one loop level. So let me explain why that is the case in detail using a Feynman diagram. So as we discussed, this muon G-2 could be in the electric symmetric notation explained by these dimension 6 operators. So from the dimension analysis and the loop counting, so here this 1 over m square m being the mass scale would be as large as 1 over 16 pi square, the loop factors and the correction couplings divided by the masses of new particles. This would be our naive expectation. And if someone asks me to estimate the G-2 in 10 seconds, this is the answer I will give. But let us compute the G-2 and see if this naive expectation is really true or not. The answer is no, as you might expect. So the quantum correction can be divided into two classes of the diagrams. One is the proportional to this Yukawa interaction. So another is proportional to this Yukawa interaction. And the first one has only one diagram. The second one has two diagrams. And for the second one, we must sum over two diagrams, of course, to maintain gauge invariance. So let's start from the first one. So here you can see that fermion-Lorentz structure is trivial. There's no Pauli matrix inside because there's no gauge boson attached to the fermions. So the fermion-Lorentz structure is trivial. So then the G-2 at amplitude level should come from this second dimension 6 operators. So which is proportional to the linear power in the momentum of the external fermion. So to compute the distance G-2, we could put Q, the momentum photon, to be 0, and look at the amplitude to the linear order in P. So let's do that. So then this is the intermediate step. So let me explain how each factor comes. This epsilon times k just comes from this part, photon, the charge Higgs interaction. And this blue part comes from just the propagators of the charge Higgs, okay, the momentum weight. And this function f comes from these propagators of the fermion, and its explicit form is given here. So here, charge Higgs, which is in anomalous boson in the standard model, is massless. But to clarify what is happening, so I will keep that mass as a free parameter for 10 seconds. So if we expand this the amplitude to the linear order in P, so here this is what we have. So here U is just k squared with the Euclidean in the signature. So then, and since we expand to the linear order in P, we have the derivative on f, the function f. So if we put the Higgs mass to be 0, as is the case for the standard model, this is an integration of the total derivative. So which pick up the UV boundary value and the IR boundary value, and which vanishes. So here you can see that it is crucial that the mass of this scalar is 0. If this extra scalar is a new particle, the mass is in general non-zero, and we obtain non-zero G minus 2. So this vanishing G minus 2 from this diagram is a consequence of no extra light scalars. So since this the fact that this function f vanishes both at UV and IR is important.
May I interrupt you?
Thank you.
Can we go back to previous slide?
This one? Oh.
Yeah, this one. Because I'm trying to say that it is much simpler than you are describing. Because no, first of all, you are implying that this implies that okay, forget about gauge coupling, right? Because it's just H. So, because in principle there is a kind of this relation between for example in unitary gauge, for example, the diagram would not exist even. You see, but because H would be having only zero charge component. But, okay, but let's take as is, as you're describing. Okay, now let's cut the loop. Let's consider diagram without photon, and it would be initial lepton, final lepton, and 3 Higgs, right?
3 one Higgs. Sorry.
1 Higgs, which is you have going down, and two other Higgs, which then form the loop. Okay.
Okay. Yeah.
So you have a diagram where you have three external Higgses and 2 leptons, right? And as you mentioned already yourself, that the structure of the diagram is such that spinor indices of these leptons are convoluted. Agree? So it means that leptons are form spin 0. Okay, and it is just 3-level effective operator, which contains 3 Higgses and leptons in spin 0 state. It is before loops. Okay, now, and it is what I am trying to say, that it is a 3-level of Wilson operator product expansion, which gives you this operator cube of Higgs field and leptons. Okay. And then, of course, you can say, let's consider matrix element of this operator, which is good photon or whatever. But however, once my leptons are in spin 0 state, then I will never generate my magnetic moment operator, whatever you do. So in this way, this cancellation is predictable.
But still, so we can just then consider the next higher dimension operator.
No, but at this level, I'm trying to say that this explains why you're getting this total derivative, because the matrix element of this operator could not produce magnetic moment, because my operator, this original operator I'm talking about, is containing spin 0 state, and you need not spin 0 state in leptons to have this magnetic dipole moment. So in this way, you are when you're calculating, it is including your loop calculation. But I'm trying to factor out this 3-level part from loop part.
But still, I mean, you're talking about dimension 6 operator here. But I mean, we could consider some higher dimension operator with extra.
No, but just a moment. It would be because at the level I can see that I did not introduce derivative external momenta, so I did not need them. At the higher loops, you probably would consider external momenta, then it would be a different story. But at the level of discussion we have now of this dimension, okay, for me, what I described it is the dimension 5 operator, right? 3H. No, it's dimension 6. The dimension 6 lepton, but the fact that leptons are entering in spin 0 state, it's enough to explain this vanishing.
that explains why there will be no logarithmic correction from that dimension 6 to dimension 6. We still have, from the Lorentz effective theory point of view, we have dimension 8 operator that can generate dimension 6 through quadratic divergence. Actually, I will get to that. That's the real point. Maybe we can discuss that again. How about that?
No, but look, I'm trying to here only focus on this particular part. I'm trying to say that there is no surprise.
No. Even for this particular part, that is not enough, because you can just simply look at a dimension 6 operator at the Lorentz effective field theory.
I'm not sure that I follow.
So what they are doing is just look at this effective operator after integration S and L, that is dimension 6, and argue that that dimension 6 operator will not generate this dimension 6 G-mass operator. That's what I agree with you. But to argue that the G-mass should vanish, we should, if you want to use the Lorentz effective theory, we must also look into the dimension 8 operator. That can generate dimension 6 operator by quadratic divergence. So
okay, just a moment. This we are talking about different stuff, because here we are talking about effect which is m mu square divided by heavy mass square, right?
However, from dimension 8 operator, if you have a quadratic divergence, you can generate dimension 6 operator. Wait. M square over m fourth. So you can't simply look at dimension 6 operator in the Lorentz effective theory.
No. Wait. It is a point which is should be clarified. Normally, well, as we discussed, the correction are of the order of mu square divided by heavy mass square, right? Okay. When you are talking about higher dimension, you are talking about correction mu to the fourth divided by mass to the fourth.
Yes, but however, if you look at the dimension 8 operator in the Lorentz effective field theory, the quadratic divergence could generate dimension 6 operator and compensate the 1 over m fourth.
I do not follow, because once we started, we found dimension 6 operator in the tree level. Okay? And I'm saying that this dimension 6 operator at the tree level does not exist. Does not exist. It doesn't contribute later on to magnetic moment. It does exist, but it contains spin zero structure out of lepton, and that's why whatever you, if you are talking about this particular dimension 6 operator, it never would generate. Okay, you still can discuss operator of higher dimension as also tree level.
So
then discuss what they will, but it would be no mixing between these two states.
No. But yeah, at the RG, no. But if you want to use that Lorentz effective field theory to show that G-minus to vanish, you must think about the quadratic divergence, which is of course absent in the Lorentz RG, but generally it exists.
Forget about divergences. You do not need to think about divergences because everything in this case is finite. Okay, because
but that divergence is actually that just the calculable, in the full theory. But my point is this quadratic divergence in the Lorentz effective theory suggests that there could be UV contribution.
But what means UV contribution? Where here everything is completely fixed because we know what is UV. Once we introduce heavy clock, we know that. So
in the minute you use effective field theory, so you can't say that this is finite. Just use dimension 6 operator. There could be the dimension 6 operator generated from the quadratic divergence and dimension 8 operator.
I think it's still not important because once you are doing this kind of Wilson operator product expansion, it is a way to account for UV, right? Because you are saying UV is provided by heavy quarks, right? And we are looking for the effect of this heavy quark. So this effect could be either mu square divided by capital M square or mu to the force divided by heavy mass for the force. And when you are trying to discuss this kind of different type of divergence, whatever, eventually the result should be formulated in terms of coefficient of quadratic mu over m or quartic mu over m. That's it. It's the answer.
In that formulation, there could be UV boundary condition of dimension 6 operator that contribute to muon G minus 2. And you can't simply look at it.
You're trying to prove that there is no mu square divided by m square, right? It is your proof. Okay, and I'm trying to give you an argument that it is indeed true. But I'm trying to say that my argument is simpler than yours.
No, okay, my argument is your argument is wrong. Yeah, no, it's not enough. It's not enough to just look at dimension 6 operator in the non-effective field theory.
Not enough in terms of if you are going after mu to the fourth divided by m to the fourth. But for the purpose of this particular consideration of one loop you did, for this purpose it's enough.
No, I disagree. I disagree.
Oh, okay, but it is. But you can disagree, but your result do agree with what I'm saying.
Okay. For example, if we take this scalar to be a new particle, and just give it non-zero mass, it generates the non-zero G minus 2.
No, but there is not. But in standard model there is no H plus.
No. But your argument seems to also forbid the G minus 2 from the new physics, even if the scalar is a new particle.
But what means new particle? We agree that in your model H plus there is standard Higgs. In the standard Higgs, you should introduce gauge interaction, and you know that you can go to the gauge where H plus is 0. Right? So why you refer to H plus, which doesn't exist in the standard model?
Then even for unitarity gauge, we have a corresponding diagram.
Yeah. Right, you should correct
that equivalence to this computation, as long as the relevant momentum is above the electric scale.
Right, but then we are talking about effect of MW. So in this way, when we are talking about normal Higgs, and you neglected MW. So in this way, you are considering the case where gauge coupling is 0. Okay, then when the gauge coupling is 0, you know, then all masses in this particular theory, you should say yourself whether it's theory with unstable Higgs, whether it's theory with vacuum average, or it's theory without vacuum average. So you did not formulate this. So your Higgs theory refers to unbroken case, right? Then.
I mean, as long as the relevant momentum is above the electric scale, this computation is also fine.
No, but we are talking at the end of the day about low energy theory. So it's important whether it's important what is the physical Higgs mass. And
as long as new physics mass scale is above the electric scale, so this diagram can be well approximated by this Goldstone boson picture. So we don't have to use W boson to see dimension 6 operators.
Okay, but okay. Either you consider standard model or you're not considering standard model. In standard model, there is no H plus. That's it.
I totally disagree, but let me proceed.
We are talking about physical particle. A physical particle you can count. In unitary gauge, it doesn't matter. You count what are physical particles in your theory.
But here, this is a computation above the electric scale. So now the Higgs picture is also good.
No, I'm not saying that it's not good, but it does not make you free from obligation to say what a physical spectrum.
Okay.
I think maybe you can continue this discussion offline, and we can continue with the talk.
We already tried it offline a little bit before.
So let's see. So since here it is important that this function vanishes both at UV and IR, So let me a little bit elaborate on why they vanishes at both UV and IR. UV is trivial. This simply comes from the calculability of the muon G minus 2 in a renormalizable theory. This is rather trivial. What is not so trivial is this function f vanishes at the IR. So in this computation, so this comes, technically this comes from the structure of the fermion propagators. So here in this fermion propagator doesn't involve the chirality freak. So when the momentum vanishes, k plus p equals 0, this trivially gives 0. So that's why this f0 equals 0. But there's more interesting way to see why f0 equals 0 from the symmetry point of view. So in the limit where the fermion momentum goes to 0, this amplitude of the contribution from this red box should be expressed by it's proportional to an effective operator without derivative on the fermion. But you can, but let's try to just construct that. But however, so here the only operator that we can write down is this one. But here, since we only use the Stan-Mori Higgs, this HH, which is contracted with the SU2 index, trivially vanishes. So this is why this F0 goes to 0. And we can again see that importance of the absence of new scalar. If this 108 is a new scalar, this identity doesn't hold. So now let's check another diagram proportional to another set of Yukawa coupling. So, but it turns out it gives the same form of the quantum correction and with the same function f. So here, the reason why f0 equals 0 cannot be attributed to the structure of the fermion propagator. Instead, that should be attributed with the fact that the operator with the derivative trivially vanishes because of this SU2 structure. So let's just look closely into this quantum correction and just look at the integrand. So integrand is of this form. So here I just express this in the log space. So x-axis is the momentum square in the log axis, and y-axis is the integrand. So you can see that integrand is non-zero at each energy scale, but the integration over it cancel between these two peaks. So here, to clarify the structure, I took the unrealistic mass hierarchy between the ML, the mass of doublet, and S, the mass of the singlet. But from this, you can see that this vanishing dimension 6 operator cannot be understood by the conventional scale by scale symmetry argument, which requires that the integrand vanishes at all energy scale.
But look, it is exactly what I said, that once you see that it is dimension 6 operator in T level contains this spin 0, then this automatically follows.
And no. Let me say more about that in a few slides. So let's see. Now let us see this integrand. What's happening in this integrand from the effective field theory point of view? So at the very low energy, so we can integrate both S and singlet. And since the dimension 6 operator vanishes trivially, so we should we have dimension 8 operators. So then this first peak in the IR could be understood by the quadratic divergence from dimension 8 operator. So we may think that by observing this quadratic divergence, we may think that, oh, then we end up with a non-zero muon G mass. But what happened is in the full UV theory, there's a cancellation between IR and UV. And the naive expectation from the very low energy effective field theory is wrong. So I have this partial answer to the Arkadiy's comments. So this is what I say. So from the Lorentz effective field theory point of view, there is this contribution from dimension 8 operator. It's not enough to see the trivially vanishing dimension 6 operator containing 3 Higgs. Do you agree or?
But the dimension 8 operator, this contains 1 over m to the 4th or what?
1 over m 4th, but could be compensated by the quadratic this divergence.
No, just a moment. No. When I'm talking about 3-level expansion, I am talking about 3-level expansion.
To 3-level. That's what I did. Dimension 6 vanishes. Dimension 8 non-vanishes.
Okay. But just a moment. Then you have 1 over m to the 8. 4th. 1 over m to the 4th, and you have extra derivative from leptons, right?
This one, yeah.
Okay, so then when you have extra derivatives of lepton, this extra derivative would be like d square acting on lepton. Okay, but d square acting on lepton, once we account for photon, then d square would be equivalent to f mu. And then I would agree with you, because then you would have operator f mu, but then the answer would be, I believe, would be like when you take in this matrix M, it would be like m mu to the 4th divided by heavy mass to the 4th, and it would be contribution to magnetic moment. So I don't, but this would be real higher dimension operator contributing to this. So I does not disagree with this, but I'm trying to say that you can start from 3-level. 3-level accounting for extra derivative, right? So instead of saying that it is quadratic divergence or whatever, you're just calculating how much this contributes.
I through you with theory, we can actually compute that. Yeah.
Right, but then what you are saying about 0 here, it is about dimension 6. It's not about dimension 8.
I don't know, but my argument here is we can't simply look at dimension 6 operator at the Lorentz effective field theory to argue that G- should trivially vanishes. Because in the Lorentz effective field theory point of view, there is a dimension 8 operator and quadratically divergent quantum correction to G-2. Which is actually manifest in this integrand. You can see that this dimension 8 operator.
You cannot argue, right? But once you calculate in coefficient for this operator, you can argue.
In Lorentz effective field theory, we can't really compute.
We have finite we have finite UV theory. There is no problem here to say what is a cutoff. So argument. So to say that there is no way to calculate this coefficient, it's not in complete UV theory. It's no. I disagree. Of course, you can calculate this.
Yeah, in complete UV we can compute that. But my argument is that you can't just look at the Lorentz effective field theory. We must look at the full theory.
Sure. No. Yeah. But it is always to calculate coefficient. You are looking to the full theory. That's true.
We really should continue with the talk.
Okay.
I mean, we've mostly spent time arguing, so no more. All right, I'll have to meet you.
Okay. Yeah.
No, but it is still important issue, because if
no, I'm serious. We have to continue with the talk. You've wasted most of the time so far.
So sorry. Yeah. Let me continue. But most important point we finish very soon. Yeah. Let's see just some comments about this phenomenology. That's also important. But yeah, let me continue.
So we have 40 more minutes. So don't worry about this. Yeah.
Okay. So yeah, this is analogous to something like this. Suppose we compute the mass difference between charged pion and a neutral pion. Then our naive expectation is their mass difference is given by the one loop factor times the cutoff scale of the QCD, which is the Low-Mason scale. So that is correct in our QCD. But this vanishing the G-2 is from the Lorentz effective theory point of view, is something like we compute the mass difference and find the value much smaller than this naive expectation. So this is a bit surprising to me. Okay. So now we have discussed a very low-energy effective field theory point of view, where we integrate both singlet and lepton, doublet. So let us now consider the case where we have doublet, singlet, and consider effective field theory in between them, where we integrate the doublet lepton. So then from this part, integrating out the lepton doublet, we obtain a dimension 6 operator shown like this. So if you compute the G-2 from this in the intermediate low-energy effective field theory, we have the correction corresponding to this first peak. Then based on this, one may think that the low-energy effective, based on the low-energy effective field theory, there will be non-zero G-2 even in the full UV theory. But what actually happened in full UV theory is this IR correction is cancelled by the UV correction. So there is some conspirational cancellation between IR and UV. And this, again, naive expectation from the IR effective field theory that doesn't work here. So, okay, well, at one loop, this vanishes. So maybe the next question, how about the two loop? Do we have the natural, does that still vanish? But the answer is no, it doesn't vanishes. The reading diagrams are the one where we add the top quark loop. That is bigger. Top quark has an order 1 coupling with the Higgs, and that gives the dominant corrections. We can insert the loop here, here, and here. That can be understood by this wave function renormalization. So the original, this du times f prime u integration involve extra factor of log, which no longer vanishes. So at the two loop level, we have non correction to the G-2. And what happened in the integrand is this IR peak and the UV peak has slightly different coefficient, and the cancellation between them is incomplete. However, for the observed value of the G-2, this two loop correction is subdominant in comparison with what we will discuss in a few minutes. So the leading one is given by dimension 8 operators, given by this. So in addition to dimension 6 operator, we just add extra 2 Higgses. So this might be the appearance of this dimension 8 operator from the viewpoint of the effective field theory may be understood as RG correction from this dimension 8 operator after integrating both new leptons to this dimension 8 G-2 operators. And in the limit where both leptons are much heavier than the W boson, we have this leading log approximation. But the exact form is not important. But since this new physics mask is not much variable with the electric scale, we should just give the full result. And this is just the formula. So as we expected, we have one loop factor and the correction of the coupling here. But
I'm sorry to that, but mu is the first power?
Sorry, mu is
the first power. It could not be.
Fifth.
Because you are saying that is v multiplied by mu, it should be mu square.
V times mu. So this mu just does not come from the coefficient of the operator, but just comes from the conversion of the dimension 6 or 5 operator to mu.
In no calculation you will get mu in the odd power. This is just technically wrong.
Mu fourth. Did you say mu fourth?
It should be not v multiplied by mu. It should be mu square.
So actually, so that extra power of mu is hidden in here.
Where?
This YA, YR.
Oh, not true. No. Why? Okay.
So here, this mu just simply comes from the. Okay, so if we express this YL, YR times YV in terms of the quantum correction to the muon mass, yes, we have m mu times delta m mu. Yeah.
Right, but then you see, it's much better to write it explicitly as a mu square, right?
M mu times delta m mu. Yeah. Correction to the muon mass.
No. Correction to mass, it's one story. Correction to delta mu, it's a mu square, because in definition it was 1 over mu when you defined what is a mu. Remember?
That definition explains this m mu. Yeah. So then here I didn't express y r times y v in terms of delta mu. Yeah. This is actually this can be expressed as m mu times delta m mu. And delta mu may be much smaller than m mu. Yeah. I agree. Yeah.
And also both operator again the same operator actually.
From viewpoint of G minus or what physically happens. Yeah. Okay. I think this is a full result. And I think since it's dimension 8 operator, this fourth power of new physics mass can appear in the downstairs. Okay. So since now let me just pause a few minutes to comment on the quantum correction to the muon mass. As we discussed, if just eliminate photon from these diagrams, so the naive correction to the G mass, so we obtain actually quantum correction to the muon mass. So then this is a formula we have formed. You can see this negative sign here. So if we explain the deviation of the G mass from the standard model prediction, this correction to the G mass must be positive. So if we choose the sign of the coupling so that the correction is positive, it turns out the quantum correction to the muon mass is negative. So this means that if we obtain the muon mass solely from this quantum correction, so we obtain the wrong sign of the quantum correction to the muon G minus 2. So we must have an extra contribution to the muon mass in addition to this quantum correction, unfortunately. So this might come from just a 3-level Yukawa coupling or come from some threshold correction at the high energy scale. But anyway, we can obtain this fully radiatively at this low energy theory. Okay, so now it's time to phenomenology. So now what's the important point is, since the quantum correction to G minus is given by dimension 8 rather than dimension 6 operator, the required mass scale of the new particle is smaller than the naive expectation. So as a result, the experiment can more easily probe the viable parameters of that theory. So here is a list of the phenomenology we consider. One is the very exciting one, direct production of the new particles at collider. So what we call L, which is the SU2 left doublet, electroweak charge, can be produced by gauge interaction at the LSC. So then we use a constraint we reinterpret the constraint on slightly different model. And this singlet does not have, of course, the gauge interaction, but still have a Yukawa coupling with the standard particle. So it can be produced via that Yukawa interaction. Now, this is a very direct constraint or prospect. So we also have some indirect constraint or prospect. So because of this Yukawa coupling between a standard particle and a new particle and a standard Higgs, after putting the non-zero wave of the Higgs, this introduces a mixing between standard particles and new particles. So what we call the muon, or what we call muon neutrino, is actually a mixture of some new particles and the very standard model particles. It's only standard model-like, but have slightly different property, such as the coupling with the W of Z boson. So this can be constrained or detected via precise measurement of the decay pattern of the electric weak gauge bosons.
But at which range you are expecting the mass to be? It is below this 100 GeV, 100 GeV before, or it's larger than 100 GeV? I mean, which direction you go?
So heavier direction, heavier than 100 GeV typically.
But heavy direction would be enough to give you observable difference for G-2, or because it would be suppressed, right? For heavy.
Yeah. But if it is too heavy, now we can't explain the muon G-2 unless we take a really large Yuga coupling. So we still have an upper bound from the mass scale.
So you are talking about 100 GeV, or you are talking about 1 PV?
Even higher one, yeah.
Higher one. Okay.
Yeah.
But your dimension 8 operator would be enough to give this for sigma deviation for this heavier part. Is what I'm wondering.
Actually, it is too heavy because of this dimension 8 operator. It cannot. So mass is abounded from above to explain the muon G-2. But then since we can't make the mass arbitrarily large, so we have non-trivial constraint. I will show the figure very soon. Yeah.
Okay.
Thanks. And we also require that Yuga coupling is perturbative and is smaller than unity. And another phenomenology we consider is so-called lepton universality. So in the standard model, the interaction of electron and muon is basically dictated by the gauge interaction. It has universal coupling to W boson or Z boson. But once we have this mixing between the thermal particle and a new particle with different gauge quantum number, so their interaction with the weak gauge boson could be deviate from the prediction of the standard model. And in particular, since we only introduce new particle to the muon sector, the interaction of muon with gauge boson in general is different from the interaction of electron with gauge boson. So this is often called the violation of the lepton universality. So for example, the decay branch of a tau lepton into mu lepton or electron lepton via double boson gate exchange provide important constraints. And
may I add something really naive? Just make sure I really follow. The capital L and S are new fermions, right?
Capital L and capital S are new fermion, and L is the SU to left charge, SU to left doublet, and S is a singlet. S, yeah.
And they are both new fermions. Both
are new fermions.
No problem. Yeah. Just make sure whether they are there's how do they satisfy, for example, like anomaly cancellation constraint.
So since we just introduced the Dirac particles, anomaly cancellation is trivially satisfied.
Okay.
Yeah.
No problem.
Thank you. Yeah. The model has a few parameters. So especially the form of the quantum correction depends on if we use this Yuga coupling, which we call YV, or different set of Yuga couplings. So, and they have different dependence. Then the quantum correction to the G-2 has a different dependence on two masses. So we will discuss two extreme cases where one is 1 and another is 0, and one is 0 and another is 1. So and we also consider the two fixing of the parameter. One, we fix the G-2. Two, we fix the quantum parameter so that the quantum correction to the muon mass is fixed. So I in total show 4 panels. So here is a plot, the case where we put one of the Yuga coupling to be 1, another to be 0, and require that the muon G-2 is explained within 1 sigma. So we fix on each point in this plane, we fix the coupling so that muon G-2 is explained. So then after that requirement, this red shaded region is excluded by the precise measurements of the W and Z boson decays. And to the right of this dashed line is excluded by the decay of the tau boson, tau lepton non-universality constraint from the decay of the tau lepton. So you may naively think that since we consider new physics, low mass should be excluded. But here, the reason why high mass is excluded is just because we fix the parameter so that the muon G mass is explained. So what happens is when we take the higher mass scale, we need a larger coupling so that the mixing between the standard lepton and the new leptons become actually larger, and the constraint from W and Z interaction becomes stronger. And this green shaded region is just excluded by the direct charge of the SU2 doublet L. And if we have some future collider, such as an international linear collider, to the right of this particle dotted line can be probed. And if we can produce 10 to the 9 of Z boson in future collider, to the right of the second dashed line, which is labeled as giga Z, can be probed. And this contour shows the contour of the quantum correction to the muon mass. So for example, on the line -30, the quantum correction to the muon mass from this theory is -30 times the observed one. So we need a fine tuning like 31 -30 equal 1. So this basically shows the degree of the fine tuning in the model. So we should look at the region where this number is small. Now you can see that all viable parameter regions can be probed by the future colliders.
I'm not sure you are talking about correction to the muon mass, but
muon mass, yeah.
But muon mass, I believe, in your formula, your divergent, right? Corrections.
Yeah. So here I fixed the cutoff scale lambda to be some value.
Right, but look, it's arbitrary fixing, right? How do you know? Because you know that strictly speaking, muon mass it's a physical input, right? It's not calculable. Right, I mean, so this way, put in some parameter. Of course, you can put some. I mean, but it's theoretical division. It's not observable effect as by itself.
Yes, I imagine that we actually have some physics, another new physics at this cutoff scale lambda. So that this is a finite correction. But still, the dominant IR dominant correction should come from this IR log running.
I agree, but look, your theory, even without introducing this additional physics at 10 to the 5th GeV, it is fully the theory is UV complete, right? You do not need to know. No, of course, it does contain necessity to introduce some physical input, right? But in this way, you are defining your cutoff by measuring mass of muon. So why it's no? I think that it is a little bit unphysical at the moment. Of course, if you would have real particles there, I would agree, right? I mean. About there, because then you indeed can differentiate, but it is not in your theory.
Not in our theory, but still we have this in IR effective theory of our theory. We have this log divergence. So in other words, which could be understood by just log running. So I think it's fair to just to show the compatibility with the possible UV theory, so that what could be the ultimate fine tuning in the model if we embed a theory into some with a theory to a theory with cutoff scale, that cutoff then correction to the muon mass. Anyway, so that's why I didn't show this, didn't shade the region with high fine tuning, because it is not clear this is really excluded or not. This only show the compatibility with the UV theory. Yeah, so we should actually look at I agree. We should actually look at this red line and the green line to definitely prove the theory. Yeah. Okay, so here is another set of coupling. So I just switch off the original coupling and just switch on this coupling. And we have
by the way, Keisuke, you can use full screen because part of the slides are blocked by on the top.
Oh, let's see. What's
Not a full screen sharing.
Like this?
A full screen.
Full screen. Let's see. Shoot. How is it now? It is still blocked, or I use full screen in my side.
I see. Maybe there should be this green, right? Green. There's a green button on the top. The left top button, left side top. There's a anyway. It doesn't really matter that much. Yeah, is that right?
Let's see. How does this look now? It's bad again. I can use this then. I think every part is now shown.
Yeah,
right?
Yeah, whatever. Yeah.
Okay. So here is basically the same figure, but for different coupling. You can again show that all parameter region can be probed. And so here, instead of fixing the muon G minus 2, so I fix the quantum correction to the muon G minus 2 while fixing the cutoff scale of the quantum correction to the muon mass. So then now this blue, instead of blue band, we can explain the muon G minus 2. And again, now you can see the thick one shows 1 sigma range and thin one shows the 2 sigma range. Then again, you can see that the future massing can probe the all viable parameter space. And and just that's the same one for the different set of the coupling. Okay. So let me give summary and give some brief discussion. So this model violates the Naturalness expectation for quantum correction to the muon G minus 2. So as a result, the required new physics mass scale becomes smaller, and the parameter space of the model can be fully probed by future colliders. So this may have some implication to the electric hierarchy. So the natural expectation would be that if there is a new physics with a cutoff at the cutoff scale lambda, we will have a quantum correction to the Higgs mass as large as 1 suppression times the cutoff scale. So this cutoff scale is, for example, the masses of super partners in supersymmetric theory. To observe the Higgs mass squared, this cutoff scale must be around the electric scale. But however, such possibility has been excluded by collider experiments. So if this natural expectation is again wrong, and we have extra suppression like the 2 factor, the masses of new particle could be 10 times larger, say 1 to 10 GeV, which is completely compatible with the collider constraint. So it might be interesting to see if there can be some new physics, if the quantum correction to the Higgs mass for the new physics is suppressed because of this total derivative phenomenon. Okay, that's all. Thank you.
Of numbers, I am sorry to just to follow. Remember, you estimate a normal correction request for 100 GeV, right? A new particle, right? I mean, new fermion, say 100 GeV. When you are talking about your correction, which has an additional mw squared divided by mu squared in addition to what it was, right? It looks like you are suppressing correction, right? Okay, so when you're suppressing correction, then your new fermion should be even lighter than 100 GeV, and I'm not sure I follow this particular part.
What's happening here is the factor of 6 here, and so I allow the quantum correction to the muon mass to be a bit larger than the that's a trick, yeah.
So essentially, you are saying that numerical coefficient is large, right?
Numerical coefficient here, yeah.
I see. Okay. Thank you.
Thank you. Yeah.
Yeah. So thank you, Keisuke, for the wonderful lecture. 素晴らしい講演のありがとうございました。
ありがとうございました。
Any question from the audience?
I didn't check chat.
I don't think nothing is important there.
But they say that when my mistake in the full screen. Oopsie. Oh.
Is Matt has a question?
Question about something entirely non-technical, but your reference to QCD and the pion mass splitting, I just didn't understand what you were saying.
So here, just what I just wanted to say. That also in the QCD, if you just look at the quantum correct naive the diagram.
By lambda QCD, you mean the cutoff on the effect of Lagrangian?
Yeah.
Okay, so it's a technical point rather than a numerical point.
Yeah. Actually, I didn't imagine the exact number. Yeah, just I mean cutoff. Yeah, like Robinson mass or new resonance scale.
But when you say it is almost like, are you saying that in a similar way there's some cancellation that?
What I meant is that this is almost like when we compute the pion mass difference in the QCD-like theory and find that the mass difference is small. Of course, this is not happening, not what's happening in the QCD, but to me, it's something like this.
But look, m rho square in QCD is proportional to lambda QCD square. So you are talking about numerical coefficient, right? Because both relations are the same relation if you have in mind.
Yeah. What I want to say, this first equation, of course, not what is observed.
No, but then your point is that mass of rho, which is proportional to lambda QCD, with coefficient which is larger than 1, right? That's it.
No. What I want to say is, I didn't argue that this is what is happening. The small correction is not what is happening in the QCD. I just wanted to say that having this small correction in this theory with vector-like fermion is, to me, almost like that the pion mass the mass difference of the pion it's small. I mean, it's not actually small. I just want to say that it's like
it's confusing here. I think what you're saying is that the surprise here would be if, in fact, contrary to fact, the pion mass splitting was even smaller.
Yeah.
That would be
all right. But it is
as if, yeah.
You need to rewrite the slide so it's a little clear what you're trying to say.
As if it were that, like that, yeah.
But Matt, look, I think you would agree that it is just a numerical coefficient between m rho and lambda QCD, right?
I'm not even talking about that's value. I'm just saying that if we find that this the mass difference is much smaller than this naive expectation in the QCD, we will be surprised. But of course, that is not what is happening in the QCD.
In other words, Akari, he's saying QCD in the real world, QCD satisfies the expectation that you would naively have.
I see.
Theory, as if you went and measured the pion mass splitting and discovered it was under.
Yeah.
Okay, I agree with this interpretation. Yeah, I agree. But look, moreover, say in QCD, some rules with, for example, no relation between lambda QCD and m rho. We are calculating. No, I mean, in certain sense.
In this lambda, I just meant that the mass is only new resonance rather than just dynamical scale. Yeah.
So I had a question, Keisuke. Hi. The place where you were showing the integrand, which was canceling between the two contributions.
This one?
Right. So this is from the full UV theory, right?
This is full UV theory, integrand, the full UV theory.
Right. So maybe you said it and I didn't understand. Can you identify what are the features of the UV theory which give rise to such a strange, surprising fact in the low energy effective field theory? Because this will kind of tell you this naive expectation, right? That when you do power counting and you say this is the contribution, but it's not correct. What kind of UV theories will fool you? Is there something you can identify with this toy model or?
What generically?
Yeah,
so
exactly.
Generically, again, if the correction is proportional to the total integration of a total derivative, we will always have this.
So that is true, but something I mean, that's technically true because that's how you're getting a UV minus IR contribution. And then you also have to have arguments to say why they're both zero, right? So you had some chirality argument or the structure of the integrand.
Both zero. Let's see.
But it is not that one UV and both UV, because you call it UV and R, but it is artificial separation of scale. If it, it is still heavy fermion scale, right? So in this way, it's about how much is UV contribution.
Well, I was referring to the slide where you had F0 and F infinity, and I think you're arguing that one is zero just because it's 2 powers in the denominator in the function u, and the other one was zero because of chirality, right? That if you set the momentum to zero.
This is not because of chirality, because of this identity of SU2.
Sorry, the SU2.
Yeah, this is not coming from chirality.
Okay, but I mean,
in general.
But my general question was the integrand being a total derivative is a bit opaque. Is there something more open that one can think about in these toy models, which will?
I don't have any other example beyond total derivative.
Let me add to this that it depends which way you are calculating diagram. When the integral is total derivative, you can use a different way of parameterizing momenta, and then this cancellation would be immediate. So this kind of technically dependent statement. However, the point itself that it is zero, it would be still true. I mean, what I'm trying to say is that it could be in much simpler way if you will do it a little bit different technically way.
That's what I don't understand. Yeah.
Well, I mean, the integrand isn't physical, right? And the answer is physical. So you have the potential for moving things around and making the cancellation look different from here. I think that's what I'm trying to explain. But,
I agree, Matt. Yeah.
I think Keisuke's question is, well, but if you're a low energy theorist, could you set up the calculation naturally in such a way that something that was obviously zero would instead start looking quadratically divergent and therefore have to So I think the problem still stands, even though your statement is true, that from the UV point of view, you can make it obvious. The question is, from the IR point of view, can it be non-obvious?
But you cannot do it without, kind of fixing the theory, right? In certain sense.
Well, if you say that if I do power counting from low energy point of view, I expect that theories in this class are going to have a divergence, and then there's one subclass that has a natural cancellation, but I haven't discovered that UV class yet. Then as a IR theorist, you might think naively, all theories in this class are going to have this problem, but then there's a really interesting subclass that doesn't have the problem. That's kind of what we'd want for the Higgs, right? Is there's some class of theories for which, even though you naively expect that all the arguments about naturalness are correct, it's got a trick up its sleeve.
No, but in this particular example, Matt, I believe that here the theory is fixed, right? And in this particular example of the theory, which under construction, which ultraviolet finite, well defined. In this particular theory, I'm looking for the term which is 1 over, say, heavy mass square. No, I mean, implying that this term is calculable, right? I mean, it's not that it's not defined. So when I believe that it's calculable, then I can try to, because if it's finite, then I can try to do it in turn. So first I am considering three-level expansion in 1 over mass square.
But even if the theory is calculable, in the minute you just use effect field theory, it's uncalculable. And you can just look at a dimension 6.
No, I can, because if matrix element of this three-level expansion is finite, then everything is well defined. You see, because then it's useful, because when I'm calculating G-2 correction from this three-level expansion, if I would will have divergences, then I would agree with what you said. But there is no divergences there. I'm trying to say that this matrix element is finite. And then everything is well defined.
What I don't understand is why you can just say that this is finite, even in the low energy fictive theory, and try to complete quantum correction.
No, because I can calculate matrix element and see that there is no divergence for these particular operators. There is no divergence.
No. But if you start from dimension 8 operator, the divergence, so things get uncalculable.
Okay. No, let's start first of all dimension 6 operator. We have 1 over m square multiplied by certain operator, and I'm saying that matrix of this operator is finite.
By the way,
but I don't understand why you can just start from dimension 6 operator in a low energy effective field theory.
Maybe let the other people ask first, and then if Keisuke has time, we can. Yeah. Okay. I do have a question. Okay. Let me ask.
Sorry. Yeah.
I have a naive question about global structure of your model. So we have a 3 generation of lepton and quarks in standard model. How many generation of this new fermions, the capital L and S you introduced?
Just to explain the muon G-2, it is enough to introduce just one set of this particle. Yeah.
Okay. And then my question is that how this make your model attractive? Maybe are there some other reasons maybe make your model you believe that make it maybe there are some fundamental reason you believe this might be it's an argument, whatever.
This could be more interesting if we can explain the Yukawa couplings radiatively. So one question in some model is why there's a hierarchy between electron Yukawa coupling, muon Yukawa coupling, and the tau Yukawa coupling. So one idea is that the Yukawa coupling of first 2 generations comes from the quantum corrections. So if we could succeed in that within this kind of model, that could explain the pattern of the flavors, and the model can be more interesting. But unfortunately, I explained, at least from the IR correction, so we cannot obtain a correct sign of the muon Yukawa coupling. So we must rely on some extra UV physics. So to make this more interesting, so maybe we should construct a theory where actually correct muon mass is obtained.
Okay, and I also have a question about. It seems like you introduced some Majorana mass coupling between the S fermions. Is that right? Are these crucial?
Majorana mass. What do you mean by Majorana coupling?
Because you have S and SC. Maybe coupled. At least on some diagram, you do have S and SC.
I introduced Dirac mass, S conjugate. Just
Dirac mass.
Okay. So if we introduce Majorana mass, I expect there is some quantum correction to the neutrino mass, thermoneutrino mass. So there will be some strong upper bound on this Majorana mass. So I just put it to be 0.
Okay. Well, thank you.
So I had another question, Keisuke, and it's related to the thing I was asking before. I think you showed in one of the slides that the 2 loop does not have this cancellation. Now, is it possible to twist around the UV model to make it cancel at 2 loop? Or is it true that if you made it cancel at 2 loop, the 1 loop would not cancel anymore? Like, is it like how much can you push this accident in the IR theory? Have you thought about it?
I have actually no idea if you can eliminate just 2 loop. Yeah, my suspicion is it will be very, very difficult. Yeah, but yeah, maybe we should think about that direction. Maybe you are imagining the pushing up the say electric cutoff scale new electric scale even higher, the 1 to 10 dB. So I don't have any good idea. Yeah, that's my honest answer.
I mean, phenomenologically, yes, but even from this aspect of understanding the UV IR structure of field theory, right? Like how much wrong can we be? Is there somehow that we cannot be that wrong, or can we be crazy wrong and it can happen at, I don't know, arbitrarily high loop or something like that? So
Can I just make a remark on that? I mean, it sort of relates to the question I was going to ask next, which is you haven't given us. I mean, you've argued to us clearly that there's no symmetry that forbids these things, right? But in the case of little Higgs, for example, there are loop suppressions that come from a spurion analysis. Right? I'm sure that you and Nima thought about that. You didn't find one. Maybe there still is one. And so I think, Rashmi, the key here would be to explain why the one loop cancellation occurs from some more principled point of view, and then you would have a chance of understanding whether it could ever continue.
Right.
But this relates to I think a question which is both relevant for Arkady and Rashmi, which is, if we indeed considered theories like this one, but also including the second Higgs doublet, now we have a much wider class of theories. And we can track them from the ultraviolet, we can track them from the far infrared, and think about what's happening. And in this subclass where either the second set of Higgs decouples due to couplings going to zero or due to their masses going to infinity, we discover that in low energy theory, something interesting happens. But we don't know why yet, right? And so from the low energy point of view, why is this subclass different from the other class, which, you just threw in some scalars and some leptons, you write down all the effective operators you should have, and something funny happens to coefficients for a reason that is not yet determined by either a symmetry or a spurion argument. And so that's kind of where, I think the attention needs to be.
But Matt, I did try to argue actually that if you consider this, in this particular theory, possible intermediate operator, which appears like linear, quadratic in fermion field and cubic in Higgs, you are finding out that this it's not a surprise. It's not it's just a statement that there is no operator contributing to G-2 at this level.
Had that argument too. He has H dagger H appearing in various places, and it's zero. But the problem is that's a UV argument.
I agree. I'm not arguing.
From the IR point of view, there's no such argument. You don't even have the field H. So how are you going to discover this from the IR point of view? That's the question.
No, I agree that in this way, it's a specific feature how heavy fermions contributed, because if they contributed only in the way when they are mixing this spin zero state for leptons, then you could be sure that it's not a problem. I agree that it is in certain way I'm fixing but I'm fixing it at the T-level expansion in heavy quark mass, right? Moreover, when we are talking about this higher dimension operator, the physical operator we are looking for, it is dimension 5 operator, right? At the end of the day, F mu multiplied by mu bar mu, right? And what we are calculating coefficient for this operator, right? At the end of the day, and when, for example, Keisuke, you are talking about dimension 8 operator. This dimension 8 converts themselves into additional smallness in this coefficient, because coefficient was a mu squared divided by capital M square. Now it is a mu squared divided by M square multiplied by MW squared divided by M square. Okay, so in this way, it is the question how to calculate from UV complete theory coefficient for dimension 5 operator, right? At the end of the day. And moreover, and your calculation refers to a smaller contribution, right? Not a mu square or M square, but a mu additional MW square or M square. And that's why, in some way, it seems to me kind of very strange to hope that it would help phenomenologically. You see, because it's more suppressed.
Yeah, for phenomenology, it's a direction where the experience can more easily discover. Yeah. But we don't have higher signal. Yeah.
Okay, but but in this sense, Matt, I see your point. I agree. But in this way, I mean, no, how to say? Once we are calculating this stuff, which is small coefficient for the same dimension 5 operator, I'm not sure that it is this type of problem you are discussing. No, that's why I kind of.
I mean, you know, there's two points of view on this talk and on their paper. One is, okay, this is interesting for G-2. It gives you a different way to think about it. The other is this gives you a different way to think about, or gives you some reason to think about naturalness a little more carefully.
Okay.
And I'm sort of taking the second point of view and not really worrying about G-2. And there the issue is, okay, what kind of mistakes can you make as an effective field theorist by not understanding what a theory can do in terms of the operators that it can generate? Right? I know about spurion analysis. I know about symmetries. So is this a third thing? Or is it really secretly a spurion analysis that I could have known already from little Higgs?
Okay, I would rather agree that it is a third thing.
And the third thing being that
it is
a certain class of operators cannot be generated. Just
you see that it is special kinematical structure, right? Because you are kind of bilinear in fermionic field in certain way. In muonic field in certain way. You see, so I think that it's a kind of a very special case.
Yeah, it still smells to me like maybe a clever, slight generalization of spurion analysis would tell you that. I mean, somehow
probably yes.
Analysis.
Yeah, because you can kind of introduce proper spurions, right? The one which would be sensitive to this.
Well, I guess that's our homework.
Right, thank you very much for everyone for the nice discussion. And I think Keisuke said that he will need to pick up his daughter.
Yeah, 8 minutes.
So let's thank Keisuke again, and then hopefully to see him again sometime. And thank you very much. Subayashi Koeno, arigatou gozaimashita. Thank you.
Arigatou gozaimashita. Thank you.
Thank you for the nice talk.
Thank you.
Stop share. I really need to go now. Yeah. So thank you. Bye. Yeah.